Okay. So let's see here. So we have to talk about how we need to how can we find the optimal parameters. So we talked about neural networks and we talked about like forward propagation and all that. But we have to go back to the problem of how we actually can find the optimal parameter. How do we find the optimal weights? Okay. So what you need to do is if you want to find the optimal weights, all you have to do is find the right set of weights that'll minimize that cost we talked about. So find the right set of weights where when you do the forward propagation of an example, you put it through the neural network and you see what the predicted output is. That error between the predicted output and the observed output should be as small as possible. And you want to sum this over all of your training examples, and then that amalgamation should be as small as possible. Okay, so we need to find the lowest cost given the weights, for every single layer. So what we need to do is we want to do something with gradient descent, where you have your cost function and you want to find the gradient with respect to the weights so that you can minimize the cost in order for you to use these weights. So we have to do that for gradient descent. So we need to find the derivative with respect to every single weights for every single weight over all layers. So what you can do is you can use batch gradient descent if you wish. Like if you took a look at logistic and linear regression, you summed over all of the training examples and computed one update. But that could take long, especially for complex networks where you could have a network with millions of neurons, and each of those neurons in turn will produce millions of weights. So if you wanted to do a batch gradient descent on a very complex neural network, it's probably going to take a while before you compute an update. So what we're going to do in this course is we're going to use stochastic gradient descent instead. So yeah, it does take a little bit, but there is a very efficient way to compute stochastic gradient descent using neural networks, and there's a very popular algorithm which is called backpropagation. Okay, so the basic idea is you're just going to take a look at one training example, you're going to put it through the neural network, use feed-forward propagation or forward propagation and figure out what the prediction error is. Using that error, you're going to figure out the right updates for all the weights in order for you to be able to minimize that particular error for that particular training example. So you have one example, figure out what the prediction error is, figure out what the weight update would be, and then you're going to repeat this for the rest of your training examples in your data set. So for each training example that you have, you compute a weight update, and then you repeat that for the rest of the training examples that you have in your data set. So then you have M updates. And then what you're going to do is you're going to go back to the beginning and start all over again. So you're going to cycle through your training set a few times or so, maybe 10, maybe 20, it doesn't matter. But you keep doing that until the weights more or less converge. Okay? And this is what is called backpropagation. There's a very efficient algorithm for computing stochastic gradient descent, which is called backpropagation. So recall the error for one example. So let's just take a look at one example for now. So we have the error, which is just the squared error between what you see for the output layer, which is x of L, and then it's the difference between the predicted value. So this is the predicted value. So this is not the output layer, and this is the true value. And you're just computing the squared error. So you're just taking each individual component. So you have, if you have an output layer of, let's say, 4 neurons, what you're doing is you're subtracting each of the components between the predicted output and the true output, just subtracting them, squaring them up, and just adding them all up. Okay? Okay. So if you have this, let's see here. So what we need to do is we have to figure out, let's take a look at, so if we're taking a look at just one example, so what we need to do is we need to compute, we're just taking a look at one example. So we want to figure out what the gradient is for. So what you're doing is you have this cost function, you want to figure out what the update is so that you can update your weights. So you have to take a look at this cost function, you have to figure out what the gradient is for that. Okay, so we need to compute this for all weights. Okay, so let's take a look at this diagram one more time. So this diagram will really help us to figure out how we can do this. Okay, so if we looking at a node, okay, so if we take a look at a node, right, when you decide to change the weight, okay, when you change the weight, what gets affected is just the input, Okay, so remember, all the inputs that are coming into this node, so you have a whole bunch of neurons here, and then they're all being submitted into this node. If you decide to change the weight, what is affected will be the inputs into this node. So that's what is being affected. Okay, looking at a node, a change in weight only affects the inputs that are coming in. Okay, so we can use the chain rule. So by chain rule, if I want to compute this guy here, this is what I need to compute, and then this will give us the update that I need. You can chain this into two operations. Oops. And this is just by chain rule. Okay? So I can take this computation, I can split up into a product of two terms by chain rule. Now, recall that this guy is just a summation of weights, right? So this is from 0 to okay? So what I want to do is I want to differentiate this guy with respect to the weight. So this is just a summation of weights. So what's going to happen is that when you differentiate this, what's going to be left is just, you have, this times this system. When you differentiate, the only thing that's going to be left is this guy here. That's with respect to I. Okay, so when you sum that up, what's going to happen is okay, because this is summation of weights, so what's going to happen is that you consider all the other terms constant except for the one that you're differentiating with. And then you're going to have a term Wijl times x. And then when you differentiate that, that becomes 1, so all you're left with is this. So then you can just substitute this into here. So therefore, okay, so I know one of the terms already, that's nice. Oopsie. Okay, but I don't know this. I'm not sure what this is. What is this? Okay, how do we find this? Okay, so I'm going to have to introduce something. So we're going to call this a sensitivity. So call this the sensitivity. Okay, so we call this a sensitivity because it's basically the change in the error. So when the input into a node changes, how will the error change? So that's how we define the sensitivity. So we define the sensitivity, so this is defined as defined as the error of one example with respect to the corresponding input signal at node J in layer L. So when a particular input changes into a neuron at layer L, how does the error change? How sensitive does the error change? So what we have to do is if we want to be able to compute this error term, so this gradient term that we're going to use to update our weights, we have to figure out what the sensitivity is for the error with respect to all the neurons that you have for every layer. So when you change the inputs into each of the neurons, how will the error change? So we have to figure that out. Okay, so we're going to define this as delta J of L. Okay, so this is equal to, okay, so this is not defined for bias units. We don't need to check how sensitive, we're just checking the other neurons, okay? So not for bias units because these never change. Because the bias units don't have any inputs, right, it doesn't make sense to do any sensitivity analysis on them because there's no way we can directly change them. It's just there's no inputs that we can use. They only give you outputs. Okay, so these never change. All right, so this is basically that stuff. So we define these as a sensitivity. So all we have to do now is compute these, and then we're done. Okay. Okay. All right. So what we're going to do now is we're going to do a little recursively. So we know that at the output layer, okay, we know that at the output layer, you're just applying the activation function on the inputs, okay, as from before. Okay. Okay, so therefore, let's take a look at just the output layer for now. So for every node for the output layer. So this is the sensitivity at the output layer. The reason why is because the output layer is actually really easy to compute, and then you have to recursively do the rest. Okay, that's good. Okay, so therefore, sorry. Okay, the chain rule, here we go. We know that. Let's see here. Okay, actually, let me just give you a little information before we start. Okay, so let me just introduce this one more time. Okay. All right. So if we take a look here, all right, so this is the output layer, right? So let's see here. Okay, so this is a sensitivity. So when you take a look at the change with respect to the inputs, so the inputs are directly related to the outputs. So when you want to take a look at how the inputs into the nodes change, they're directly related to the outputs that come from all the other nodes. Okay, so by the chain rule, let's see here. Yes, the error depends on, each of the inputs, right? Directly through okay? All right, so therefore, okay, we had this guy. Okay, and then we can apply chain rule again. So, yep. So this is chain rule stuff. Okay, so we can actually compute these, no problem. Okay, so here, well, this is actually quite simple. We know that from here, we have this relationship here. Okay, so what this is telling us is that it wants us to find the derivative with respect to S of j. Well, that's pretty simple. This is just equal to, okay, because if I know that this is related to this, okay, this is saying that I need to differentiate x with respect to s, and that's pretty easy. It's just the derivative. So that's no problem. This goes in here. Okay? Now this is saying that we need to differentiate the error with respect to the input. So if you remember what the error was, it was all the way up here. Sorry, this guy here. What this is saying is that I need to take this function and differentiate it with respect to x. So in that case, everything goes away except for the one that I want. So when you differentiate, you have the two cancels, and then I'm just left with this product here by itself, or one of them anyway. So when you do that, what we get is okay, and then you multiply this by. Okay, that's pretty good. So this is what it would be for the output layer. Right? Okay, so that's the output layer, that's good. So if I want to compute the sensitivities, all you have to do is for every single neural nut chart for the output layer, just take what the predicted value would be at the output layer for, for node J, subtract it with its true output, and then multiply by the derivative of the input. Okay, and that's fine. Okay, so in general, you can pretty much apply this to any layer that you want. Okay, so this is equal to, okay, and then, all right. Okay, so what you can do here is using the sensitivities from the output layer, what you can use this and propagate it backwards. So the reason why it's called backpropagation is because starting from the output layer, you calculate the sensitivities for the layer L-1, and then L-2, then you keep going all the way to the beginning. Because what you're doing is you're kind of taking the neural network and reversing itself. You're backpropagating from the output back to the input. Okay, so yeah, there's a lot of theory here, but I'll solidify it with an algorithm at the end. Using the sensitivities, delta JL, for every node at the output layer. Okay, output layer. We find all of the other layers. So we find all the other layer sensitivities. So we can finally compute this term, the gradient term for the error for all weights. Okay? Then do the update. So that's stochastic gradient descent through backpropagation. Okay? So basically what I mean is that we know this already. We can compute that quite easily. Then all you have to do now is solve for the second highest layer and then the third highest layer all the way down to the first one. Okay? Okay. So now what I'm going to do is I'm going to solve it in general, and then I'll give you what the algorithm looks like. So, therefore, let's solve for sensitivities other than layer L. Okay? All right. So let's take a look at the previous layer for now. So at node J of the, of a previous layer, okay? So we have this guy. Oops, this is partial, sorry. What was it? It was, okay, and then we can split this up by the chain rule, because the input here actually depends on the output of the previous layer. All right, so this we know from before. This is pretty easy. It's just the derivative of the activation function. Okay. All right, so let's take a look at this one more time. Okay, so what's happening here now is that I need to figure out what this guy is. Right? So I have to do another chain rule, and I'll talk about this soon. All right, so basically what's happening here is this output, so at a particular, let's say, what is it, J? Yeah, I guess we can do J. Sure, J is fine. So let's say I've got some node J over here, for now. Okay? So what's going to happen is that the output of this contributes to all the other nodes in the next layer. Okay? So what's going to happen is that because this sensitivity for this output is being forwarded to all the other neurons in the next layer, what's going to happen is that we have to sum all of the contributions that this neuron makes with the next layer. So we're going to have to do a recursive chain rule. So since the output of xjl minus 1 contributes as an input into each node, Sj of L, right, for all the nodes, for j is equal to 1, 2, up to as many nodes as there on that layer. Okay? We need to add all the contributions. So it's just using chain rule again. Yeah, if this is confusing, don't worry about it. Just we'll talk about the formula at the end. Okay? So therefore, looks like I'll do an example next class. It looks like I don't have time today. So what I need to do now is I have to add up all the contributions that this node sends to all the other neurons in the next layer. So okay, and this is just application of chain rule. Okay, alrighty. So let's see here. Okay, so if you take a look, each of these inputs here, right, they're being sent to all the other neurons except the bias unit. So there's no bias unit that's being sent. So that's why we're starting from 1, because there's no bias unit contribution. Okay, so you've got that. Okay, so this here is just the sensitivity at the current layer. So this is delta K of L, right? And then this guy here, well, if you remember what the summation was, you have, this is just summing up all the inputs. So I've got K is equal to 0 to D of L, right? I'm just using a different summations index here. Okay, so if I differentiate this with respect to x of j of L, the only thing I'm left with is, oopsie. Okay, so that's what I'm left with. Because what you're doing is you're differentiating, all you're left with is this. Okay, so therefore, all right, so this is equal to, let's see here. Okay, that's fine. Let me just write out the actual summation. So I have the sensitivity for this guy now. So hold on a minute. This is, okay, so I'm going to split this up. Okay, this I know from before. So this is just, I'm just going to rearrange the product. Okay, and then this guy is just the above, which is so this is delta. All right. Okay. Okay, so now that we have this, finally, if I want to compute the error, okay, this is simply, we split it up as before. Okay, so this is defined as the sensitivity. We talked about that. So this is delta J L, and then this is x of IL minus 1 from before. So this is from before. And this is definition. Okay. So what does this tell us? All right, so this stuff was calculated from forward propagation. So you have to save all of the inputs and the corresponding outputs. And then this stuff here was from backpropagation. So if you want to compute an update for the weights, you have to run forward propagation and remember all of the saved outputs, you know, the X's for every single neuron. And then you have to compute the sensitivities by backpropagation. So for one update for the weight, you have to run a forward propagation and a backpropagation to be able to find all those updates for the weights. Okay, so therefore, we must run. Okay, so then what I'll do is I'll show you a linear algebra shortcut, and then I'll call it a day. I'll have to do an example next class. So we must run forward propagation. And remember, we'll see if I can try to do it quickly. Remember all the, you know, the xj's and the s of j's, okay, before computing the gradients. So it's actually, you know, it looks like it's a bit of work, but it's actually much more computationally saving than actually trying to do batch gradient descent. Okay, so here's the actual final algorithm. Here we go. So this is the backpropagation algorithm. Okay, to compute. So this is what we need. We need the actual gradients for the cost function for every single weight that we have. So in order to be able to compute an update for gradient descent. So the first step that you have to do, okay, what you need to do is you need to provide a training example. So backpropagation to compute, this is for one example. Okay, so you need a training example first, okay? And then what you got to do is you have to set input layer to X, all right? The next step that you have to do is use forward propagation to save results at each layer. Okay, so you're going to need, so you have to save Sj and Xj for L is equal to 1, 2, up to L, and for as many neurons as there are for each layer. Okay? So you got to use forward propagation to save all those, so you have the inputs that are coming in as well as the corresponding outputs. Okay? And then what you need now is you have to do backward propagation. So what you have to do is you have to initialize sensitivities for output layer L. Okay? So in that case, it's this guy. So it's just x of j L minus y of j, and then times the derivative of the activation function for the input signals going in. So you have to initialize the sensitivities for the output layer. And then finally, you have to compute sensitivities for the other layers, except for the input. That's all that is just, it's just going out. There's no inputs going in. Okay? Compute sensitivities for the output layers. So for the second highest layer, third highest layer, all the way down to the first hidden layer, you want to compute their sensitivities. let's see here. 1, and this is 10, and then, okay, so those are the sensitivities there, okay, and then finally compute the gradients. Okay, so which is this? So it's just sensitivities of layer L, and then corresponding input. All right. Yeah, that is a lot of work. Okay. Let me just share the linear algebra viewpoint, and then I'll call it quits. I'll do a detailed example next class. Okay. So let me just end this talk with linear algebra viewpoint, and we'll call it a day. And this is the one that I'll expect you to remember. It's actually, when you do it with via linear algebra, it's actually very simple. Okay, so what we're going to do is we're going to take a look at the sensitivities, at a layer that's not at the output. So let's look at not at the output layer. Okay. All right, so it looks something like this. Okay, and L plus 1. All right, so if you want to compute the sensitivities, you have to look at the next layer and propagate backwards, right? Let's see, yes. Okay. Okay, so let's break this up very slowly. So if you take a look at this, all right? Well, if you take a look at this summation here, this is simply the weight matrix for that particular layer, L plus 1, but you're not considering the first row, because the first row is considered all the bias units, so we're disregarding the first row. So W, J of K, L plus 1 is the weight matrix W, L plus 1 without the first row. Yeah, I'm almost done here. I got maybe a couple more slides and we'll call it a day. Okay, so what I'm going to do is I'm going to call this W tilde, L plus 1. Okay, so this is to symbolize that remove the first row. Okay? And then, so that's this one, and then delta K. Right, so this is what we can do is we can collect all values into a vector. So what this is doing is that you can represent all the sensitivity values for the next layer into one vector. Okay, collect all values into, so this is the sensitivities for layer L plus 1, all right? And then finally, Sj of L, right? So these are the input signals into layer L. Okay, we can collect this into a vector. And I'm just going to call it S of L. All right? Okay. So what we can do is we can finally represent this as a very simple matrix multiplication. So if you take a look at this summation on the right, this is very simply a matrix multiplication or matrix vector multiplication. So this here is a vector, right? And this here is a matrix. So if you actually work this out, this is a matrix vector multiplication where you take the weight matrix, remove the first row, and multiply this with a sensitivity vector that's for the L plus 1th layer. Okay? And then what you can do is this creates a vector, and then what you do is you would element-wise product with this guy, which produces another vector as well. So, okay, so let's see here. If we can use the active or the derivative of the activation function. G of Z in an element-wise manner. Therefore, these sensitivities can be found by this, in this way. I'm almost done. You can wait outside, please. Thank you. Okay, so this is what it would be. Okay, this guy here, this is what is known as an element-wise product. It's also what's known as a Hadamard product. So for example, let me just give you a quick example so we know what we're talking about. So for example, if I had a vector, let's say this is 1, 2, 3, and I had another vector which was 4, 5, 6, okay? If I did A element-wise B, what you're going to do is you're going to produce another vector that is the same size, where you take one element, multiply by the corresponding element, and that's the result. So 1 times 4 will be 4, okay? 2 times 5 is 10, and 3 times 6 is 18. So that's what the element-wise would be. So what you're doing is you have vectors of the same size, you multiply each of the elements correspondingly, and then you produce a result. Okay? All right. I've got a few more minutes and then we'll end it. Okay, so I just want to write down some final observations and then we'll call it quits. Okay? Now look at the gradients. Okay? So if you remember, this is equal to sensitivity. And then what I can also do is these products are commutative, so I can switch these and they'll give you the same thing. Okay? So what we can do is we can take these updates and we can place them into a matrix of the same size as defined by the shape of this layer. Okay, so we can place this in matrix form. To be the same size as the weight matrix defined at that, for that shape. Okay, indexed by I and J, right, for row and column. I'm almost done. All right, just want to lay out this diagram and I'll do an example, okay? So in this case, oops, it's going to look like this. Right? So the X values are the rows and the sensitivities are the columns. Okay, so this is x1, x of d of minus 1, previous layer. Right, and this is x1 and so on and so forth. So it looks like that. Okay, so what you can do here is you can represent this matrix as the outer product of two vectors. So given, let's say A0, A1, M. And let's call this B0, B1, N. Okay? What you can do is if I took A and multiplied it by B transpose, this is what's known as the outer product, or the dyadic product. Okay? So if I took B, I transposed it and I multiplied it, what you would get is a matrix of pairs of combinations. So you get A0, B0, A0, B1, A0, Bn. This is A1B0, A1B1. Okay, all the way down to here, and all the way down this way. I'm almost done. Yeah, I got a few minutes. Sorry, thank you. I'm almost done. Okay, so if you take a look, if I represented the x vector and sensitivity vectors, and if I did the outer product, what will happen is that if you did the outer product between these two vectors, you'll actually get exactly that matrix. Okay, so therefore, the outputs of layer L minus 1 are collected into a vector, right? Okay, therefore you can compute the sensitivities quite easily. X of L minus 1, and then times the sensitivity vector transpose. Okay. Okay, I'm just going to write the backprop algorithm one more time. Got a couple minutes left, and we're going to call it a day, all right? I ran out of time, unfortunately. I wanted to do a nice example, but we'll do that next time. Okay. Step 1, initialize. So provide training example. And set input layer to x0. Okay? There's 3 more steps, and then we're going to be done. So use forward prop and save results. So I need XL and SL for L is equal to 1 to all the way up to L. Okay. Find sensitivity vector for the output layer, okay, which is okay, and element-wise, okay, and then finally, compute sensitivities. Actually, I'm missing one more step, and I'll do that quickly. Equals, this is prime here. Great. Element-wise. I'll do an example next class. I'm running out of time, unfortunately. Okay, and then finally, last step, compute gradient. So this is for L is equal to 1 to up to L. Okay, so that's it. I'll do an example next class. I unfortunately ran out of time. But this would be the backpropagation algorithm for linear algebra. Okay? Okay, thanks a lot. I'll see you next class.